The combustion chamber, or combustor, must contain the burning mixture of air, which is being passed from the compressor, and fuel, from the fuel spray nozzles, in order to generate the maximum heat release at a substantially constant pressure, so that the turbine receives a uniformly expanded, heated, and accelerated stream of gas. This is not an easy task, but advancements are constantly being made in combustion chamber design to enable more efficient use of fuel with less and less pollution of the atmosphere. Efficient combustion has been made increasingly more important because of the rise in the cost of the fuel, and also the increasing awareness of the aviation industry and the general public of the dangers of atmospheric pollution from the exhaust smoke. There is the limit to the maximum temperature of the gas exiting from the combustion chamber. This is imposed by the materials from which the nozzle guide vanes and the turbine blades are manufactured. The slightest excursion above that temperature limit will mean distortion of the turbine blades and the possible disintegration of the turbine, with probably catastrophic results. Modern turbine and nozzle guide vane materials will allow a gas temperature not exceeding 1700 degrees Celsius when it exits the combustion chamber. Considering that the air which leaves the high-pressure compressor may already have been heated to around 550 degrees Celsius during its compression, we can add sufficient fuel to raise the temperature of the gas exiting the combustion chamber by a further 1150 degrees Celsius, before we exceed the limit temperature of 1700 degrees Celsius. It must also be remembered that the combustion chamber has to be capable of maintaining stable and efficient combustion over a wide range of engine operating conditions. Of course, 1700 degrees Celsius would be the temperature of the gas exiting the chamber with full power selected. Lower power settings would require lower fuel flows, and consequently would generate lower gas temperatures. You'll see from this graph that the air enters the combustion chamber at a slightly slower rate than which it enters the intake of the engine. Speeds of around 500 feet per second are not unusual. The flame rate of kerosene, that is, the speed at which the leading edge of a flame would travel through kerosene vapor, is approximately 30 feet per second. If burning kerosene was exposed to an airstream which was travelling at 500 feet per second, it would be extinguished immediately. So, something must be done to slow down the speed of the airflow after it leaves the compressor, and before it reaches the combustion chamber. Otherwise the flame would not be sustainable. At this position on the graph we see how this reduction in the velocity of the air is achieved. The air is slowed down, and, an added bonus, its pressure is increased after it leaves the compressor by passing it through a divergent duct immediately before it enters the combustion chamber. In fact, the pressure attained at this point, at the end of this divergent duct, just before the air goes into the combustion chamber, is the highest in the whole of the engine. The reduction in velocity is still not enough, however. Further decreases must be achieved if the flame is not to blow out. The air is divided after it exits the high-pressure compressor into primary, secondary, and tertiary airflows. We'll now examine each of them. This diagram shows how the air entering the flame tube passes through the snout before being divided to go through the perforated flare and the swirl vanes and into the primary zone. The primary zone is a region of lower velocity recirculation, positioned immediately downstream of the fuel spray nozzle. It's within this zone that stable combustion is achieved. The primary air is approximately 20% of the total airflow coming from the high-pressure compressor and into the combustion chamber. This is the air which is mixed, in a ratio of approximately 15:1 by weight, with the fuel and burnt. By being passed through the flare and the swirl vanes, the velocity of the primary air is reduced, which must happen if the flame is not to be extinguished, and the shape and position of the flare and swirl vanes also starts the air recirculating within the region. The remaining 80% of the output of the high-pressure compressor, air which has not been directed through the snout, goes into the space between the flame tube and the air casing. Some of this remaining air, approximately another 20% of the output of the high-pressure compressor, is allowed into the flame tube through secondary air holes. This air is called secondary air, and it reacts with the primary air, which is flowing through the swirl vanes to form a toroidal vortex. The toroidal vortex stabilizes and anchors the flame, and prevents it being moved through the flame tube away from the fuel nozzle area. The temperature of the gases at the center of the primary zone reaches about 2000 degrees Celsius. This is far too hot for the materials of the nozzle guide vanes and turbine blades, so a further drop in temperature is required before the gases can be allowed to exit the combustion chamber. The remaining 60% of the total air coming out of the high-pressure compressor is progressively introduced into the flame tube through corrugated joints and dilution air holes in the flame tube. This air is called tertiary air. Tertiary air is used to cool both the air casing and the gas exiting the chamber. The type of combustion chamber which we have used to illustrate the interaction of the flame and the cooling air is representative of those which would have been used in an early multiple combustion chamber system. Different methods of keeping the combustion chambers from overheating are used. Some flame tubes have ceramic-coated tiles fixed to a skin on their interior walls. Cooling air passes through the holes in the skin and flows between the skin and the tile, which has a ridged surface. The ridged surface improves the heat transfer between the tile and the air. The air finally enters the flame tube at the front and rear of the tile and forms an insulating film for the tile as it flows over it. Other engine designs use a different method of cooling the air casing, which is called transpiration cooling, where a film of air flows between laminations, which form the flame tube wall, and then exits the laminations to form an insulating film of air within the flame tube. This picture illustrates several other features of the type of combustion chamber which would be used in a multiple combustion chamber system. Although the engine would probably start quite readily with only one igniter operating, most gas turbine engines have two igniters. However, because there are only two igniters, another means of passing the starting flame between the combustion chambers in this type of system has to be found. This is called the interconnector. Immediately after light-up, the flame in the combustion chambers which have the igniters causes an increase in the pressure within those chambers. The pressure differential between a chamber which has a flame in it and those adjoining it which have no flames drives the burning gases through the interconnector pipework. When the burning gases come into contact with any unlit mixture in the adjacent combustion chamber, they ignite that mixture. This process is continued around the engine until the contents of all of the chambers is burning, whereupon the pressures within them are equalized and the flow through the interconnectors ceases. The sealing ring at the turbine end of the combustion chamber allows for elongation of the chamber due to expansion. The chamber is fixed at the compressor end by being bolted onto it, and it cannot expand in that direction. The sealing ring allows the chamber to expand into the nozzle box, which is the portion of the engine immediately preceding the nozzle guide vanes, while maintaining a gas-tight seal between the chamber and the atmosphere. The straight-through flow multiple combustion chamber system was developed from Sir Frank Whittle's original design, which was supplied with air by a centrifugal compressor. The straight-through combustion chamber system was later used on some earlier types of axial flow engines, and is still in use on centrifugal compressor engines such as the Rolls-Royce Dart. The multiple combustion chamber system consisted of a number of the individual combustion chambers, which are shown here. Each combustion chamber consists of a flame tube, which has its own air casing. The combustion chambers are disposed around the engine just to the rear of the compressor section. This picture shows a multiple combustion chamber system similar to that used in the Rolls-Royce Avon, which was a powerful, for its time, axial flow compressor engine used on many different types of aircraft, both military and commercial, fighter and transport, for a considerable number of years. Shown here are the snout, the primary air scoop, the interconnectors, and the drain tubes. The drain tubes allow the drainage of excess fuel from the combustion chambers in the unlikely event of the engine failing to start, an event which is more commonly called a wet start. A wet start happens when the mixture of air and fuel in the combustion chamber fails to ignite during a start. A considerable amount of fuel will have been fed into the combustion chamber during the attempt to start. If that fuel is not removed before the next attempt to start, and if that attempt is successful, the result will be a combination of excessively high gas temperatures in the turbine region and torching, which is the name for a very long, very hot and very dangerous jet of flame issuing from the rear of the engine,